Subscribe to the channel so you don't miss out on any of these videos. Imagine standing in a vast, dark forest, surrounded by the faint glow of distant fireflies. You're aware that life is teeming all around you, but you can't quite see it clearly. This is what the universe feels like when we peer into the places where stars are born, massive cosmic nurseries filled with the raw materials for creation. These places, called stellar nurseries or molecular clouds, are some of the most mysterious and awe-inspiring regions in the universe. What's happening inside them is nothing short of magic on a scale that's almost impossible to comprehend. These clouds of gas and dust are not just celestial decorations. They are the factories of the universe, where the light of future stars is forged from the darkness. But what's really going on in there? How does a star, something so massive and powerful, come from seemingly nothing? To understand these stellar nurseries, we need to zoom out and then zoom in. Imagine a patch of the night sky that seems quiet and empty to the naked eye. With the right telescope, that empty patch might reveal clouds of gas and dust stretching across light years. These molecular clouds are cold, dark, and dense regions of space, made mostly of hydrogen molecules with traces of helium, carbon, oxygen, and other elements. They can be hundreds of times more massive than the Sun, but their density is spread out so thinly that if you stood inside one, you might not even notice it. But appearances are deceiving. These clouds are cradles of energy and potential. Inside them, gravity begins to play its quiet yet relentless role. Small regions of these molecular clouds start to clump together under their own gravity. The clumps grow denser and hotter, pulling in more material, and eventually forming what's known as a protostar, a baby star still wrapped in its cocoon of gas and dust. It's not a quick process. From the time a molecular cloud starts collapsing to the birth of a fully formed star can take millions of years. Imagine a timescale so vast that a single second in this process feels like an eternity to us. Yet, when we look at the results, those glittering points of light that fill our night skies, it feels like time itself disappears. One of the most fascinating things about these stellar nurseries is the sheer variety of shapes and colors they take on. Nebulae, the glowing remnants of these nurseries, are often illuminated by the young stars they produce. The iconic Orion Nebula, for example, is one of the most photographed regions of the sky, and it's a stellar nursery in action. This nebula, located about 1,350 light-years away, is a bustling hub of star formation. Inside, we can see stars in every stage of their life cycle, from newborns just beginning to shine to older stars that are on their way out. But what's driving this whole process? The key players are gravity and something called turbulence. While gravity works to pull the gas and dust inward, turbulence stirs things up, creating chaotic motions that can either speed up or slow down star formation. Imagine pouring cream into a cup of coffee. It swirls and mixes chaotically, much like the gas and dust in a stellar nursery. This turbulence creates dense regions within the molecular cloud, which eventually become the seeds for new stars. There's also an incredible interplay of energy within these nurseries. As the protostar forms, it starts heating up, and its radiation begins to push away the surrounding gas and dust. This feedback can sometimes stop further star formation in its tracks. It's almost like the star is fighting back against its own birthplace, reshaping its surroundings as it grows. The result? A cosmic landscape that looks like a painting come to life, with vivid colors and intricate patterns. One of the most mysterious aspects of stellar nurseries is their role in creating not just stars but also planets and, potentially, the conditions for life. As the gas and dust swirl around the forming star, some of it flattens into a spinning disk. This is where planets are born. Tiny grains of dust stick together, growing into pebbles, then rocks, and eventually full-fledged planets. In some cases, the materials in these disks contain the building blocks of life, complex organic molecules that might one day lead to life as we know it. What's even more mind-boggling is that everything we see around us, including ourselves, owes its existence to these processes. The elements that make up your body, carbon, oxygen, nitrogen, were all forged inside stars. Those elements were released into the universe when stars exploded in massive supernovae, and they eventually became part of new stars, planets, and ultimately life. It's a cosmic recycling program that has been going on for billions of years. But despite everything we know about stellar nurseries, there's so much we don't understand. For instance, what triggers the collapse of a molecular cloud in the first place? Sometimes it's a nearby supernova shockwave or a collision with another cloud, but other times, the process seems to start spontaneously. And then there's the question of why some clouds produce clusters of stars while others form just a few. These are mysteries that astronomers are still working to unravel, using tools like the James Webb Space Telescope, which can peer into these dense clouds with unprecedented clarity. What makes this topic so endlessly fascinating is that it connects the smallest scales with the largest. The birth of a single star can tell us about the evolution of entire galaxies. It's a story that's still being written, and every new discovery adds another layer of complexity to our understanding of the universe. So, the next time you look up at the night sky, remember that every star you see had a beginning. Somewhere in the cold, dark reaches of space, it was born out of chaos and turbulence, shaped by forces both gentle and violent. And somewhere out there right now, new stars are being born, hidden from view, waiting for their moment to shine. When we look at stellar nurseries, it's like peeking behind the curtains of the universe, getting a glimpse of its most intimate and awe-inspiring processes. These regions are not just scientific phenomena, they're cosmic masterpieces, living works of art sculpted by gravity, radiation, and the interplay of countless particles. Their beauty captivates both scientists and casual stargazers alike. But the science behind their formation is as intricate as it is captivating. Let's dive deeper into what makes these regions so special. Molecular clouds, the precursors to stellar nurseries, are some of the coldest places in the universe, with temperatures often dipping to just a few degrees above absolute zero. This extreme cold is essential because it allows the gas and dust within these clouds to clump together rather than bouncing apart when they collide. This clumping is the first step toward the eventual formation of stars. But not every part of a molecular cloud gets to participate in this process. Only the densest regions, where gravity manages to overcome the outward pressure of turbulence and temperature, collapse to form stars. These dense pockets are known as Bach globules, and they are the cradles where new stars come to life. As a Bach globule collapses, it begins to spin faster, a phenomenon caused by the conservation of angular momentum. Think of it like an ice skater pulling their arms and during a spin. The tighter they pull in, the faster they rotate. This spinning motion flattens the collapsing material into a disk, a structure that will play a crucial role in shaping the future solar system. At the center of this disk, a protostar forms, steadily gaining mass as it accretes material from its surroundings. The gravitational energy of this accretion is converted into heat, causing the protostar to shine faintly, though not yet with the brilliance of a true star. The transition from a protostar to a fully fledged star happens when the core temperature reaches a staggering 10 million Kelvin. At this point, nuclear fusion ignites, fusing hydrogen atoms into helium and releasing an immense amount of energy. This marks the star's birth, and the moment it joins the cosmic tapestry as a luminous point of light. From this point forward, the star will spend billions of years in the main sequence phase, burning hydrogen and emitting light and heat. But the story doesn't end with the star's birth. Stellar nurseries are often home to entire clusters of stars that form together from the same molecular cloud. These clusters can range from a few dozen stars to thousands, all bound together by gravity. Over time, some of these clusters will disperse as their stars drift apart, while others may remain tightly bound, forming globular clusters that orbit galaxies like ancient relics. As fascinating as all of this is, stellar nurseries also have a way of humbling us. They remind us that the universe operates on scales and timescales that are almost incomprehensible. The Orion Nebula, for instance, spans over 24 light-years across. To put that into perspective, light, the fastest thing in the universe, takes 24 years just to cross its length. And the processes within these nebulae unfold over millions of years. What we see in the sky today is just a snapshot, a single frame in a movie that has been playing for billions of years and will continue long after we're gone. And then there's the sheer diversity of stellar nurseries. Take the pillars of creation in the Eagle Nebula, for example. These towering columns of gas and dust are so dense that they're actively forming stars within their shadows. The interplay of light and shadow and images of the pillars of creation isn't just beautiful, it's a testament to the dynamic processes shaping the universe. Meanwhile, regions like the Carina Nebula showcase a more chaotic side, with powerful stellar winds and intense radiation carving out intricate shapes and triggering new waves of star formation. We also can't overlook the role of massive stars in shaping their nurseries. These giants, which are often among the first to form in a new stellar cluster, emit intense ultraviolet radiation and powerful stellar winds. This radiation can ionize the surrounding gas, causing it to glow, and creating the striking colors we associate with nebulae. At the same time, the stellar winds push away gas and dust, sometimes triggering the collapse of nearby regions and jump-starting the formation of new stars. It's a cosmic chain reaction, a cycle of destruction and creation that has been ongoing for billions of years. But these processes don't just shape stars, they shape entire galaxies. Stellar nurseries are critical to understanding how galaxies evolve over time. In spiral galaxies like our Milky Way, molecular clouds are concentrated along the spiral arms, creating a pattern of star formation that gives these galaxies their distinctive appearance. In irregular galaxies, star formation is often more chaotic, with pockets of activity scattered across their irregular shapes. By studying stellar nurseries, astronomers can piece together the story of how galaxies grow, change, and sometimes even collide with one another. And what about our place in all of this? Our own sun was born in a stellar nursery roughly 4.6 billion years ago. Though the molecular cloud that birthed it has long since dissipated, traces of its origin remain. The elements that make up the Earth, and everything on it, were forged in earlier generations of stars and dispersed by stellar winds and supernova explosions. Our solar system, like countless others, is part of this grand cycle of creation and destruction. As we continue to study stellar nurseries, we're not just learning about how stars form, we're uncovering the origins of the universe itself. Each new discovery adds another piece to the puzzle, bringing us closer to understanding the cosmos and our place within it. These nurseries remind us that the universe is both vast and intimately connected, with processes happening on the largest scales influencing the smallest details. And yet, despite all we've learned, stellar nurseries remain enigmatic. Every answer we uncover leads to new questions. Why do some molecular clouds collapse to form stars while others don't? How do magnetic fields influence star formation? And what role do these processes play in the larger context of cosmic evolution? The more we learn, the more we realize how much we still don't know. The questions surrounding stellar nurseries are as vast as the nebulae themselves. For instance, one of the greatest mysteries revolves around the triggering mechanisms for star formation. We know that molecular clouds can remain stable for millions of years, but something must disturb this balance to ignite the collapse into stars. Astronomers theorize that nearby supernovae, the explosion of massive stars, could act as catalysts. The shockwaves from these explosions ripple through space, compressing the gas and dust in molecular clouds and kickstarting the birth of new stars. However, the specifics of these interactions are still not entirely understood. Magnetic fields also play an enigmatic role in these nurseries. Observations have revealed that molecular clouds are threaded with weak magnetic fields, which seem to influence the movement and collapse of gas and dust. In some cases, these fields appear to support the cloud against gravitational collapse, delaying or even preventing star formation. In other scenarios, they align the collapsing material, shaping the resulting stars and their surrounding disks. But measuring these magnetic fields is incredibly challenging, and scientists are only beginning to grasp their significance. Another layer of mystery lies in the composition of the gas and dust within stellar nurseries. These clouds are not uniform. They contain a rich mix of elements and molecules, including hydrogen, helium, carbon monoxide, and more complex organic compounds. Understanding the chemistry of these clouds is critical because it affects the formation of planets and, potentially, the emergence of life. For example, some molecules found in these regions, such as amino acids, are considered the building blocks of life. Studying how these molecules form and survive in the harsh environments of space could provide clues about the origins of life on Earth and elsewhere. But the story doesn't end with the formation of stars and their surrounding disks. As protostars grow, they often eject material in spectacular jets that can extend for light years. These jets are driven by the intense magnetic fields and rapid rotation of the protostar, and they play a crucial role in shaping the surrounding environment. By clearing out excess gas and dust, these jets help regulate the growth of the star and influence the distribution of material in the emerging solar system. Observing these jets provides a window into the earliest stages of stellar and planetary evolution. And let's not forget the breathtaking visuals of stellar nurseries. The vibrant colors we see in images of nebulae are not just for show, they reveal critical information about the composition and processes within these regions. For instance, the red hues often indicate the presence of ionized hydrogen, while blues and greens can signal the presence of oxygen or other elements. These colors are the result of photons being emitted as atoms and molecules absorb and release energy, a process that tells astronomers about the physical conditions in these nurseries. Advanced telescopes like the James Webb Space Telescope have revolutionized our ability to study these regions. With its infrared capabilities, the telescope can peer through the thick layers of dust that obscure stellar nurseries in visible light, revealing details that were previously hidden. This technology has already provided unprecedented views of regions like the Tarantula Nebula, showcasing hundreds of newborn stars and their surrounding environments in exquisite detail. These observations are not just stunning, they're rewriting our understanding of how stars and planets form. One of the most profound aspects of studying stellar nurseries is the sense of connection they inspire. When we look at these regions, we're seeing the same processes that created our Sun and solar system billions of years ago. Every star, planet, and even the atoms in our bodies have their origins in these cosmic cradles. It's a humbling reminder that we are, quite literally, made of star stuff. But stellar nurseries are not just about the past, they're also windows into the future. By studying these regions, scientists can predict how galaxies will evolve over billions of years. They can trace the cycles of star formation, destruction, and rebirth that drive the cosmos. And they can explore the potential for life in other parts of the universe, guided by the knowledge that the same processes that created Earth might be occurring in countless other stellar nurseries across the galaxy. Despite all this progress, stellar nurseries continue to challenge and inspire us. Their sheer scale and complexity remind us of the vastness of the universe and our place within it. They are a testament to the power of nature, capable of creating beauty and order out of chaos. And as we continue to explore and understand these regions, we are not just learning about the stars, we are learning about ourselves and our connection to the cosmos. It's a journey that will never truly end. With each new discovery, we peel back another layer of mystery, only to find more questions waiting beneath. But that's the beauty of science. It's not just about finding answers. It's about embracing the unknown and pushing the boundaries of what we thought was possible. And in the case of stellar nurseries, the possibilities are as limitless as the stars themselves. The more we explore stellar nurseries, the more profound their significance becomes. At the heart of these cosmic regions lies a truth about the universe. It is in a constant state of evolution and transformation. Stars are not just born in these nurseries. They grow, age, and ultimately die, recycling their material back into the cosmos. This endless cycle of creation and destruction is the very engine of the universe, driving its growth and complexity. Take the process of feedback within stellar nurseries, for example. Newly formed stars, particularly the massive ones, emit intense radiation and unleash powerful stellar winds. These forces carve out cavities in the surrounding gas and dust, creating striking structures like the bubbles seen in the Rosette Nebula. This feedback process can halt star formation in some areas by dispersing the material needed for further collapse. But paradoxically, it can also trigger star formation in neighboring regions by compressing the gas and dust. This dual role of feedback highlights the delicate balance of forces at play in stellar nurseries. Massive stars also play another critical role. They forge the heavy elements that make up planets, moons, and even life itself. During their short lifespans, these stars fuse lighter elements like hydrogen and helium into heavier ones, such as carbon, oxygen, and iron. When these stars reach the end of their lives, they explode as supernovae, scattering these elements into space. This material becomes part of the next generation of stars and planets, continuing the cycle of cosmic evolution. Without this process, the universe would lack the diversity of elements necessary for the complexity we see today. This recycling of material is not just a scientific curiosity, it's a profound connection that ties us to the cosmos. The iron in your blood, the calcium in your bones, and the carbon in your DNA were all forged in the hearts of ancient stars. These elements were then scattered into space by supernovae, incorporated into a molecular cloud, and eventually became part of the Earth and everything on it. When we study stellar nurseries, we are not just observing distant regions of space. We are exploring the origins of our very existence. The role of molecular clouds in this process cannot be overstated. These vast reservoirs of gas and dust are the raw material from which stars and planets are made. But their properties and behaviors are far from uniform. Some clouds are relatively quiet, with little star formation activity, while others are bustling with newborn stars. What causes these differences? Scientists believe that factors like turbulence, magnetic fields, and external pressures all play a role. For instance, clouds near the spiral arms of a galaxy may experience more star formation due to the increased density and compression in these regions. One particularly intriguing aspect of molecular clouds is their filamentary structure. Observations with instruments like the Herschel Space Observatory have revealed that these clouds often form long, thin filaments, with star formation occurring preferentially along their densest regions. These filaments appear to be shaped by the interplay of gravity, turbulence, and magnetic fields, creating a sort of cosmic scaffolding for star formation. Understanding these structures is key to unraveling the mysteries of how stars and planetary systems form. And then there are the outflows. As young stars accrete material, they often eject some of it in the form of powerful jets and winds. These outflows interact with the surrounding environment, creating shockwaves that can light up the gas and dust in spectacular ways. These interactions can be both constructive and destructive. On one hand, they can clear away material that might otherwise fall onto the star, regulating its growth. On the other hand, they can compress nearby regions, triggering new rounds of star formation. Observing these outflows provides valuable insights into the complex feedback processes that shape stellar nurseries. Stellar nurseries also offer a glimpse into the origins of planetary systems. The disks of gas and dust that form around young stars are the birthplaces of planets. Over time, particles within these disks collide and stick together, gradually growing into larger bodies like asteroids and planets. The composition and structure of these disks can vary widely, depending on factors like the mass of the star and the chemical makeup of the surrounding material. By studying these disks, astronomers can piece together the story of how planets, moons, and other celestial bodies form and evolve. These processes are not limited to stars like our Sun. Stellar nurseries are also home to the formation of more exotic objects, such as brown dwarfs, objects that are too massive to be planets but too small to sustain nuclear fusion in their cores. These failed stars occupy a unique niche in the cosmic ecosystem, and their formation raises intriguing questions about the boundaries between stars and planets. As we continue to push the boundaries of observation and technology, our understanding of stellar nurseries will only deepen. Future telescopes, like the upcoming Nancy Grace Roman Space Telescope, promise to provide even more detailed views of these regions, allowing us to study their structures and dynamics with unprecedented precision. These advancements will help answer long-standing questions and undoubtedly raise new ones, keeping the field of astrophysics vibrant and full of discovery. But beyond the science, there's a profound emotional resonance to these regions. Stellar nurseries are a reminder of the beauty and creativity inherent in the universe. They show us that even in the cold, dark reaches of space, there is light, warmth, and the potential for life. They are a testament to the resilience of matter and energy, constantly transforming and renewing itself in the face of entropy. When we look at images of stellar nurseries, we're not just seeing astronomical phenomena, we're witnessing the universe at its most poetic. These regions are not static, they are dynamic, alive with the processes that create stars, planets, and the building blocks of life. They are a cosmic reminder that creation and destruction are two sides of the same coin, and that from chaos can come extraordinary beauty and order. And in studying them, we are not just learning about the cosmos, we are learning about ourselves. Stellar nurseries are a mirror, reflecting the interconnectedness of all things, from the smallest particles to the largest galaxies. They remind us that we are not separate from the universe but an integral part of its story, a story that began in the stars and continues to unfold with each new discovery. The study of stellar nurseries extends far beyond just understanding star formation. These cosmic cradles serve as laboratories for testing some of the most profound theories about the universe. For instance, they give us insights into the interplay between gravity, radiation, and magnetic fields on a massive scale. Each factor contributes to the intricate dance that governs how stars are born, how they interact with their surroundings, and how they influence the evolution of galaxies. Let's dive deeper into one of the most fascinating aspects, the role of turbulence within molecular clouds. Unlike the turbulence we associate with Earth's weather systems, turbulence in molecular clouds occurs on a colossal scale. Gigantic streams of gas collide and swirl under the influence of gravity, creating regions of varying density. These chaotic motions are crucial because they can both trigger and inhibit star formation. High-density regions may collapse under their own gravity to form stars, while less dense regions may remain inert for millions of years. Understanding this turbulence is like trying to solve a cosmic puzzle, where the pieces are constantly shifting. One tool scientists use to study these turbulent environments is spectral line analysis. By observing the specific wavelengths of light emitted by molecules within these clouds, astronomers can determine their motions, temperatures, and chemical compositions. Molecules like carbon monoxide, CO, and ammonia, NH3, are particularly useful because they emit in the radio part of the spectrum, which can penetrate the thick dust that obscures visible light. These observations reveal the intricate dynamics within molecular clouds, showing how gas flows, fragments, and eventually gives birth to stars. Another intriguing element in the star formation process is the role of magnetic fields. Although invisible to the naked eye, magnetic fields thread through molecular clouds, influencing their evolution in subtle but significant ways. Magnetic fields can provide resistance to gravitational collapse, acting as a stabilizing force that prevents the cloud from fragmenting too quickly. At the same time, these fields can channel the flow of material, guiding the formation of filaments and other structures within the cloud. Recent advances in polarized light observations have allowed scientists to map these magnetic fields in stunning detail, revealing their importance in shaping the structure and behavior of stellar nurseries. The variety of stellar nurseries is another captivating aspect of this phenomenon. Some, like the Orion Nebula, are relatively nearby and densely populated with young stars, making them ideal for detailed study. Others, like the Tarantula Nebula in the Large Magellanic Cloud, are far more massive and contain clusters of exceptionally hot and massive stars. Each type of nursery provides unique insights into the diversity of star-forming environments across the universe. The Orion Nebula, for example, is a treasure trove of information. Located about 1,344 light-years away, it's one of the closest star-forming regions to Earth and has been studied extensively. Within its boundaries, astronomers have identified protoplanetary disks, or proplyds, which are the early stages of planetary system formation. These proplyds are illuminated by the intense ultraviolet radiation from nearby massive stars, giving them a striking appearance. Observing these structures helps scientists understand how planets form and how they might survive in the harsh environments around young, massive stars. In contrast, the Tarantula Nebula, located in the Large Magellanic Cloud some 160,000 light-years away, represents a much more extreme environment. This nebula is home to some of the most massive stars known, including our 136A1, which is over 300 times the mass of the Sun. The intense radiation and stellar winds from these giant stars create a turbulent and energetic environment, where star formation proceeds at a breakneck pace. Studying such regions helps us understand the upper limits of star formation and the impact of massive stars on their surroundings. Then there are the more mysterious regions, like the dark molecular clouds that remain largely hidden from view. These clouds, such as the Pipe Nebula or the Coal-Sack Nebula, are so dense that they block out visible light from background stars, appearing as dark voids in the night sky. These regions are thought to be in the early stages of star formation, where the conditions for collapse are just beginning to take shape. Observing these clouds in infrared and radio wavelengths allows astronomers to peer inside and uncover the processes that lead to the birth of stars. A particularly intriguing subset of stellar nurseries is those associated with giant molecular clouds, GMCs. These behemoths, spanning tens to hundreds of light years, are the most massive reservoirs of star-forming material in galaxies. The Milky Way contains several prominent GMCs, including the Carina Nebula and the Perseus molecular cloud. These clouds are not only factories for star formation but also key players in the life cycle of galaxies. By forming clusters of stars, they contribute to the overall structure and dynamics of their host galaxies, influencing everything from spiral arm formation to the distribution of chemical elements. As we peer deeper into the universe, stellar nurseries also offer tantalizing clues about the conditions in the early cosmos. By studying distant star-forming regions, astronomers can glimpse what the universe was like billions of years ago, when galaxies were young and star formation was at its peak. Observations of these distant regions suggest that star formation in the early universe was far more intense and chaotic than it is today, driven by higher gas densities and more frequent galaxy collisions. This brings us to the concept of universal evolution. Just as life evolves on Earth, the universe itself evolves over time. Stellar nurseries are a key component of this evolution, transforming raw material into stars and planets that may one day host life. They remind us that the cosmos is not a static backdrop but a dynamic, ever-changing entity. Every star born in a stellar nursery represents a new chapter in this cosmic story, a beacon of light in the vast darkness of space. But the story of stellar nurseries is far from complete. There are still countless mysteries to unravel, from the precise mechanisms that trigger star formation to the fate of the material left behind after stars form. Future missions, such as the James Webb Space Telescope, are poised to revolutionize our understanding by providing unprecedented views of these regions in infrared wavelengths. These observations will shed light on the earliest stages of star formation, revealing processes that are currently hidden from view. The promise of future discoveries in stellar nurseries extends beyond mere observation. Advanced simulations and computational models are pushing the boundaries of our understanding, allowing researchers to recreate the star formation process in virtual environments. These simulations incorporate data from molecular cloud dynamics, turbulence, magnetic fields, and feedback mechanisms from existing stars. By comparing these models to real observations, scientists can refine their theories and address lingering questions about how stars are born, evolve, and influence their environments. One of the most intriguing unsolved questions is the exact process by which massive stars form. While the formation of smaller stars like our Sun is relatively well understood, the birth of stars many times its mass remains a puzzle. The intense radiation pressure from these stars should theoretically blow away the material needed for their growth, yet they somehow continue to accumulate mass. Observing massive star-forming regions like those in the Tarantula Nebula can provide crucial insights, but a definitive explanation still eludes us. Additionally, stellar nurseries play a crucial role in understanding the formation of planetary systems. Observations of protoplanetary disks have revealed an incredible diversity of structures, including gaps, rings, and spiral arms, which are thought to be caused by the gravitational influence of forming planets. These observations not only help us understand how our own solar system came into existence, but also provide context for the thousands of exoplanets discovered in recent years. The interplay between young stars and their surrounding disks is a critical area of study, as it holds the key to unlocking the origins of potentially habitable worlds. The relationship between stellar nurseries and the larger galactic environment is another area ripe for exploration. For instance, in the Milky Way, star formation is often concentrated along the spiral arms, where the density of gas and dust is highest. This correlation suggests that the structure of a galaxy can directly influence where and how stars form. Galactic collisions and mergers, which were more common in the early universe, can also trigger massive bursts of star formation by compressing gas clouds and creating ideal conditions for collapse. These events, often referred to as starburst galaxies, are some of the most luminous objects in the universe and provide a dramatic example of the connection between galactic dynamics and stellar nurseries. Another fascinating aspect of stellar nurseries is their role in enriching the interstellar medium with heavy elements. Stars produce elements like carbon, oxygen, and iron through nuclear fusion, and when they die, they return this material to space through supernovae and stellar winds. This cycle of creation and destruction ensures that each subsequent generation of stars forms from increasingly enriched material, paving the way for complex chemistry and the potential for life. Stellar nurseries are therefore not just cradles of star formation but also factories for the elements that make up everything we see around us, including ourselves. The aesthetic beauty of stellar nurseries cannot be overstated. Nebulae like the Eagle Nebulas, pillars of creation, or the vibrant hues of the Lagoon Nebula are some of the most breathtaking sights in the cosmos. These stunning visuals are not just for show, they provide a wealth of information about the physical processes at play. The colors of a nebula, for instance, are determined by the types of atoms and molecules present and the way they interact with radiation. Hydrogen, the most abundant element in the universe, emits a characteristic red glow, while oxygen can produce brilliant shades of green or blue. By analyzing these colors, astronomers can infer the composition and physical conditions within these regions. As technology advances, the methods for studying stellar nurseries continue to evolve. Instruments like the Atacama Large Millimeter/Submillimeter Array, ALMA, and the European Extremely Large Telescope, ELT, are providing unparalleled resolution and sensitivity, allowing scientists to study the finest details of star-forming regions. These tools can peer through the thick dust that obscures optical observations, revealing the hidden processes that drive star formation. The combination of observational data, theoretical models, and laboratory experiments is painting an increasingly detailed picture of these enigmatic regions. The mysteries of stellar nurseries extend into philosophical and existential realms as well. These regions remind us of the cyclical nature of the universe, where stars are born, live, and die, only to give rise to new stars and planets. They underscore the interconnectedness of all things, from the simplest hydrogen atom to the most complex life forms. By studying these cradles of creation, we are not just learning about stars, we are learning about ourselves and our place in the cosmos. As we look to the future, the potential for discovery seems boundless. Upcoming missions like the Nancy Grace Roman Space Telescope and the next generation of ground-based observatories promise to unlock even more secrets about stellar nurseries. These facilities will enable us to study star formation in unprecedented detail, from the initial collapse of molecular clouds to the emergence of fully formed stars and planetary systems. The data they provide will not only answer existing questions but also raise new ones, ensuring that the study of stellar nurseries remains a vibrant and dynamic field for generations to come. Even with all the knowledge we've gained, the story of stellar nurseries is far from complete. Each discovery opens new doors, offering a glimpse into the intricate and often mysterious processes that shape the universe. These regions are not just the birthplaces of stars, they are the birthplaces of wonder, curiosity, and a deeper appreciation for the cosmos. As we continue to explore and understand these celestial nurseries, we are reminded of the infinite complexity and beauty of the universe we call home. The story of stellar nurseries is not just one of creation but also one of profound transformation. Within these cosmic cradles, matter, energy, and gravity weave together a tapestry of processes that span millions of years. These processes are not static. They are dynamic and constantly evolving, shaped by both internal mechanisms and external influences. Take, for example, the role of feedback from newly formed stars. As a young star ignites, it begins emitting intense ultraviolet radiation and powerful stellar winds. These forces can carve out cavities within the surrounding gas and dust, creating stunning bubble-like structures. The famous Rosette Nebula is a prime example of this phenomenon, where stellar winds from a central cluster of young stars have hollowed out the surrounding material, leaving a spectacular, flower-like formation. But this process is a double-edged sword. While the energy from young stars can trigger further star formation in some regions by compressing nearby gas, it can also inhibit star formation by dispersing the material needed for future stars. Supernovae add another layer of complexity to this feedback loop. When massive stars reach the end of their lives, they explode with immense force, sending shockwaves through the surrounding nebula. These shockwaves can compress gas clouds, igniting new waves of star formation, or they can disperse the gas entirely, halting the process. The interplay between star formation and feedback mechanisms is a delicate balance, one that scientists are still working to fully understand. One particularly intriguing aspect of stellar nurseries is the role of magnetic fields. Though invisible to the eye, magnetic fields thread through molecular clouds, influencing the movement and behavior of gas and dust. Observations have shown that these fields can slow down the collapse of a cloud, acting as a counterforce to gravity. In some cases, they even guide the flow of material, creating intricate, filamentary structures within the cloud. Recent advances in polarimetry, a technique that measures the orientation of light waves, have allowed astronomers to map these magnetic fields in unprecedented detail, revealing their critical role in the star formation process. The chemistry of stellar nurseries is another fascinating area of study. These regions are rich in a variety of molecules, from simple ones like hydrogen and carbon monoxide to complex organic compounds that serve as precursors to life. These molecules form on the surfaces of dust grains or in the gas phase, depending on the local conditions. Observations with radio telescopes like ALMA have detected molecules such as methanol, formaldehyde, and even amino acids in star-forming regions. The presence of these complex molecules raises exciting questions about the potential for life beyond Earth. Could the building blocks of life be widespread throughout the galaxy, seeded by stellar nurseries? The diversity of stellar nurseries is also worth exploring. While some, like the Orion Nebula, are relatively close to us and easily studied, others are much farther away and only recently becoming accessible to our instruments. In galaxies beyond the Milky Way, we find extreme star-forming environments, such as those in starburst galaxies or interacting systems like the antennae galaxies. These regions often exhibit rates of star formation far exceeding those in our own galaxy, providing unique opportunities to study the limits of star-forming activity. Looking at stellar nurseries across different epochs of the universe offers yet another dimension to our understanding. In the early universe, molecular clouds were likely denser and more turbulent, conditions that could have led to the formation of massive stars and star clusters at an accelerated rate. Observing these distant star-forming regions is challenging due to their vast distances, but advancements in infrared and millimeter-wave astronomy are allowing us to peer back in time to study these ancient nurseries. The interplay of time and scale in stellar nurseries is a humbling reminder of the vastness of the cosmos. A single star-forming region can span tens or even hundreds of light years, and the process of star formation can take millions of years. Yet within these immense timescales and spaces, the delicate dance of physics and chemistry unfolds with precision, giving rise to some of the most awe-inspiring phenomena in the universe. As we delve deeper into the mysteries of stellar nurseries, we find ourselves grappling with fundamental questions about existence itself. What drives the universe to create? Why do stars form in some regions and not others? How do the processes within these nurseries connect to the broader evolution of galaxies and the cosmos as a whole? These questions remind us that science is as much about seeking answers as it is about embracing the unknown. The future of stellar nursery research is as bright as the stars they birth. Upcoming missions and technologies promise to revolutionize our understanding, from next-generation telescopes like the James Webb Space Telescope, JWST, and the Extremely Large Telescope, ELT, to advances in computational simulations that allow us to recreate the conditions within molecular clouds. These tools will enable us to probe deeper, see clearer, and understand more fully the processes that govern these celestial cradles. In contemplating stellar nurseries, we are reminded of our own origins. The elements that make up our bodies, the carbon in our cells, the oxygen we breathe, the calcium in our bones, were forged in the hearts of stars. Stellar nurseries are not just the birthplaces of stars. They are the forges of the universe, crafting the building blocks of everything we know and everything we are. The understanding of stellar nurseries also forces us to reconsider humanity's place in the grand scheme of things. These magnificent regions reveal the cyclical nature of existence: birth, life, death, and renewal. When stars form, they breathe new life into their surroundings, but their eventual demise through supernovae or stellar winds redistributes their enriched material, seeding the next generation of stars and planets. This continuous cycle speaks to the interconnectedness of the cosmos, a profound reminder that everything in the universe, including us, is interconnected through time and space. In addition to this philosophical significance, stellar nurseries are central to understanding one of humanity's oldest questions: how life emerges in the universe. The chemical richness of these regions provides clues about the origins of organic compounds that may be precursors to life. Spectroscopic studies of star-forming regions have identified molecules like glycolaldehyde, a simple sugar, and other complex organic compounds that play key roles in biological processes. These findings suggest that the chemistry of life may begin in the vast, cold clouds where stars and planets form, long before a planet like Earth even exists. Furthermore, stellar nurseries provide a backdrop for studying the extremes of physical conditions. Temperatures in molecular clouds can drop to just a few degrees above absolute zero, while the energy released during the birth of massive stars can heat nearby material to millions of degrees. These extreme environments challenge our understanding of physics and chemistry, pushing the limits of what molecules and structures can endure. For instance, icy mantles on dust grains within these clouds can shield fragile molecules, allowing them to survive long enough to participate in complex reactions. At the same time, high-energy radiation can fragment these molecules, creating entirely new compounds. The interplay between these processes shapes the unique chemical signatures of each stellar nursery. The spatial structure of these nurseries is another area of fascination. Observations reveal intricate networks of filaments, knots, and bubbles within molecular clouds. These structures are not random. They are shaped by the forces of turbulence, gravity, and magnetic fields. Filaments, in particular, play a critical role in star formation. Dense filaments often serve as the sites where gravity overcomes other forces, allowing gas to collapse and form stars. The Herschel Space Observatory provided groundbreaking insights into this filamentary structure, showing that filaments are a universal feature of star-forming clouds across the Milky Way. These discoveries are reshaping our understanding of the initial conditions that lead to star formation. Zooming out, stellar nurseries also influence the larger galactic environment. The energy released by star formation and subsequent stellar deaths can regulate the evolution of galaxies. For example, the energy from young stars and supernovae can drive large-scale outflows of gas, known as galactic winds, which can quench star formation in certain regions. On the other hand, this energy can also compress gas clouds elsewhere, triggering new waves of star formation. These processes create a feedback loop that shapes the overall structure and behavior of galaxies. Understanding how stellar nurseries fit into this broader context is a major focus of modern astrophysics. Technological advancements have been instrumental in uncovering the secrets of stellar nurseries. Instruments like the Atacama Large Millimeter/Submillimeter Array (ALMA) and the Very Large Telescope (VLT) have allowed us to study these regions in unprecedented detail. By observing at wavelengths that penetrate the dense dust, these tools reveal the hidden structures and dynamics of star-forming regions. Meanwhile, computational models are becoming increasingly sophisticated, simulating the collapse of molecular clouds, the fragmentation into protostars, and the impact of feedback mechanisms. These models are invaluable for testing theoretical predictions and interpreting observational data. The role of dark matter in star formation is another frontier of research. While dark matter does not interact with light, its gravitational influence is crucial in shaping galaxies and their star-forming regions. The distribution of dark matter affects how gas is concentrated within galaxies, which in turn influences where molecular clouds and stellar nurseries form. By studying the connection between dark matter and star formation, astronomers hope to uncover deeper insights into the structure and evolution of the universe. The aesthetic allure of stellar nurseries also serves a unique purpose, inspiring humanity. Images of nebulae like the Carina Nebula or the Horsehead Nebula have captivated people for generations, igniting curiosity and wonder about the universe. These images, captured by observatories like the Hubble Space Telescope, are not just scientifically valuable. They are culturally and emotionally resonant. They remind us of the beauty and complexity of the cosmos, sparking questions that drive the pursuit of knowledge. As the study of stellar nurseries progresses, the importance of collaboration becomes increasingly evident. Projects like the Event Horizon Telescope and international space missions require the combined efforts of scientists, engineers, and institutions from around the world. This collaborative spirit reflects the universal nature of the questions being asked. The mysteries of stellar nurseries are not bound, they belong to all of humanity. Ultimately, the study of stellar nurseries is a testament to the human drive to understand the universe. These regions are not just the birthplaces of stars. They are crucibles of creativity, laboratories of physics and chemistry, and windows into the fundamental processes that shape existence. Each discovery in a stellar nursery brings us one step closer to answering the profound questions about where we come from, where we are going, and what it all means. The more we study stellar nurseries, the more we realize that they are not isolated phenomena but deeply interconnected with the life cycles of galaxies, the origins of planetary systems, and even the potential for life itself. These massive molecular clouds, filled with gas and dust, act as the universe's primordial factories, producing the elements and conditions necessary for everything we observe today. One particularly compelling aspect of stellar nurseries is their connection to planetary formation. While stars form in the dense cores of molecular clouds, the surrounding material often flattens into a rotating disk called a protoplanetary disk. These disks are the birthplaces of planets, moons, and other celestial bodies. Observations of these disks in regions like the Taurus molecular cloud have revealed structures such as gaps and rings, which are believed to be early signs of planet formation. ALMA has provided high-resolution images of these disks, showing that the process of star formation is intrinsically linked to the origins of planetary systems. The chemistry within protoplanetary disks is another fascinating area of research. These disks contain a mix of gases, ice, and dust particles, which interact under varying temperatures and pressures. In the outer, colder regions of a disk, water and other volatile compounds freeze onto dust grains, forming icy mantles. Closer to the star, these ices evaporate, enriching the gas phase with complex molecules. This chemical diversity sets the stage for the formation of planets with different compositions. The study of protoplanetary disks not only helps us understand our own solar system's history but also provides clues about the potential for habitability in other planetary systems. Beyond individual systems, stellar nurseries play a significant role in shaping the structure of galaxies. The Milky Way, for example, contains vast networks of spiral arms, within which most star-forming regions are located. These arms act as density waves, compressing gas and triggering the collapse of molecular clouds. This process gives rise to clusters of young stars, which in turn light up their surroundings, creating iconic features like the Eagle Nebulas. Pillars of creation. These illuminated pillars are dense regions of gas and dust, sculpted by the intense radiation from nearby massive stars. The interconnected nature of star formation and galactic evolution is also evident in starburst galaxies. These galaxies experience intense episodes of star formation, often triggered by interactions or collisions with other galaxies. In these extreme environments, the rate of star formation can be hundreds of times higher than in a galaxy like the Milky Way. Studying these starburst regions provides unique insights into the limits of star-forming activity and the role of external influences in shaping stellar nurseries. The study of stellar nurseries is not without its challenges. Observing these regions requires instruments capable of detecting faint signals across vast distances, often in wavelengths invisible to the human eye. Infrared and radio wavelengths are particularly important, as they can penetrate the dense clouds of dust that obscure visible light. Instruments like the Spitzer Space Telescope and ALMA have revolutionized our ability to study these hidden regions, revealing the intricate processes at work within molecular clouds. Future advancements in technology promise even greater discoveries. The James Webb Space Telescope, JWST, is expected to provide unprecedented views of stellar nurseries, allowing us to peer deeper into these regions and study their earliest stages of star formation. Ground-based observatories like the Square Kilometre Array, SKA, will complement these efforts by mapping the distribution of gas and dust across entire galaxies. These advancements will not only deepen our understanding of stellar nurseries, but also provide a more comprehensive view of their role in the cosmos. The importance of theoretical models and simulations cannot be overstated. While observations provide snapshots of star-forming regions at different stages, simulations allow scientists to recreate the entire process under controlled conditions. These models account for a wide range of factors, including gravity, turbulence, magnetic fields, and chemical reactions. By comparing simulation results with observational data, researchers can test hypotheses and refine their understanding of the underlying physics. One of the most exciting frontiers in stellar nursery research is the study of their role in the early universe. During the first billion years after the Big Bang, the universe's first stars, known as population 3 stars, began to form. These stars were massive, short-lived, and composed almost entirely of hydrogen and helium. Unlike modern stars, which form in metal-enriched environments, population 3 stars emerged in pristine conditions, marking the beginning of the cosmic star formation cycle. Studying the remnants of these ancient stellar nurseries could provide crucial insights into the origins of galaxies and the chemical enrichment of the universe. On a more philosophical note, the study of stellar nurseries evokes a sense of wonder and humility. These regions remind us that the universe is a place of constant creation and renewal. From the ashes of previous generations of stars, new stars and planets arise, continuing the cycle of cosmic evolution. This process mirrors the cycles of life and death that we observe on Earth, suggesting that the principles governing the cosmos are deeply universal. As humanity continues its journey of discovery, stellar nurseries will remain a focal point for understanding our place in the universe. They are more than just beautiful sights captured by telescopes. They are the crucibles where the raw materials of existence are forged. Each new discovery in these regions brings us closer to answering the profound questions about the origins of stars, planets, and life itself. The mysteries of stellar nurseries are far from solved, and that's what makes them so compelling. Each unanswered question is an invitation to explore further, to look deeper, and to learn more about the universe we call home. These cosmic cradles are not just the birthplaces of stars, they are the birthplaces of possibility, the starting points for the endless journey of exploration that defines us as a species. Stellar nurseries are cosmic time capsules, holding the secrets of creation and evolution within their dense, enigmatic folds. Despite the significant advances in technology and theoretical modeling, many aspects of these regions remain shrouded in mystery. For instance, while we understand the broad strokes of star formation, the intricate details of the interplay between gravity, turbulence, and magnetic fields in molecular clouds are still a subject of intense debate. One persistent question involves the role of turbulence in these environments. Turbulence acts as a double-edged sword. It can both prevent and promote star formation. On the one hand, turbulence generates chaotic motions that counteract gravitational collapse, delaying the process. On the other hand, it can create localized regions of high density, effectively kickstarting the collapse that leads to star formation. Understanding this paradox requires more detailed simulations and observations, particularly at smaller scales, where these forces interact most intricately. Another open question pertains to the initial mass function, IMF, a fundamental concept in astrophysics that describes the distribution of masses among newly formed stars. Observations reveal a consistent pattern. Most stars form with relatively low masses, while only a few grow into massive stars. But why this distribution exists, and whether it is universal, remain unclear. Stellar nurseries across different environments, such as the dense, metal-rich clouds in the Milky Way versus the more pristine conditions in distant galaxies, could provide clues about how the IMF is shaped. The study of feedback mechanisms in stellar nurseries is equally crucial. Massive stars exert a powerful influence on their surroundings through radiation, stellar winds, and eventually supernova explosions. These forces can either quench or trigger further star formation, depending on the local conditions. For example, the intense radiation from a massive star can erode nearby gas clouds, halting the formation of new stars. Conversely, the same radiation can compress distant regions of the cloud, initiating the collapse of new stellar cores. These dual effects highlight the complexity of feedback processes and their role in shaping the life cycle of molecular clouds. The concept of triggered star formation adds another layer of intrigue to this feedback loop. In some cases, external forces such as shock waves from supernovae or collisions between molecular clouds can compress gas to the point of gravitational collapse. This phenomenon has been observed in regions like the Orion Nebula, where evidence suggests that nearby massive stars influence the formation of subsequent generations of stars. Triggered star formation underscores the interconnectedness of stellar nurseries, showing how events in one region can ripple outward, influencing distant areas and perpetuating the cycle of creation. The relationship between magnetic fields and star formation is another area ripe for exploration. Observations have shown that magnetic fields pervade molecular clouds, influencing the motion of gas and dust. These fields can act as a counterbalance to gravity, slowing down the collapse of clouds and regulating the rate of star formation. However, when magnetic fields weaken or become twisted, they can also facilitate the collapse of specific regions, leading to the formation of stars. The exact role of magnetic fields in these processes remains one of the most challenging puzzles in the study of stellar nurseries. Moving beyond individual processes, the role of stellar nurseries in the broader context of cosmic evolution cannot be overstated. These regions are not just local phenomena but integral components of the universe's grand narrative. The first galaxies, for example, were likely dominated by massive stellar nurseries, producing stars at rates far higher than what we see today. These early star-forming regions contributed to the reionization of the universe, a pivotal event that transformed the cosmos from a dark, neutral state into the bright, ionized one we observe now. By studying stellar nurseries, we can trace the origins of these transformative epochs, linking the small-scale physics of star formation to the grand-scale evolution of the cosmos. Another fascinating aspect of stellar nurseries is their potential role in the search for extraterrestrial life. The organic molecules found in these regions, such as amino acids and hydrocarbons, are the building blocks of life as we know it. These molecules form in the icy mantles of dust grains within molecular clouds, where they are shielded from harsh radiation. As stars and planets form, these molecules can be incorporated into nascent planetary systems, potentially seeding them with the ingredients for life. Understanding the chemical complexity of stellar nurseries not only informs us about the conditions for life in our solar system, but also provides a framework for evaluating the habitability of exoplanets. The future of stellar nursery research is promising, thanks to the advent of new technologies and collaborative efforts in the scientific community. Instruments like the James Webb Space Telescope, JWST, and upcoming ground-based observatories will offer unprecedented views of these regions, allowing us to study their properties in greater detail than ever before. These advancements will also enable us to probe the most distant stellar nurseries, shedding light on the conditions in the early universe. Additionally, interdisciplinary approaches combining astrophysics, chemistry, and computer science are likely to yield new insights. Machine learning algorithms, for instance, are increasingly being used to analyze the vast datasets generated by telescopes, identifying patterns and anomalies that might otherwise go unnoticed. These tools can help us uncover subtle relationships between different properties of stellar nurseries, advancing our understanding of these complex environments. The study of stellar nurseries is a journey into the heart of creation, revealing the forces that shape not only stars but the galaxies and planets that orbit them. These regions are both ancient and ever-changing, embodying the dynamic nature of the universe. As we continue to unravel their mysteries, we are reminded of the profound interconnectedness of all things, a theme that resonates across the cosmos and within ourselves. Ultimately, stellar nurseries are more than just astronomical phenomena. They are a testament to the universe's ability to create and renew. Each star that forms in these regions is a new chapter in the cosmic story, a spark of light in the vastness of space. By studying these celestial cradles, we not only deepen our understanding of the universe but also our appreciation for the intricate web of connections that make it so extraordinary. The incredible complexity of stellar nurseries extends far beyond the birth of individual stars. These environments are not static. They are active, dynamic regions that are constantly evolving. In fact, the interplay between star formation, star death, and the surrounding interstellar medium can dramatically reshape the molecular clouds and their surroundings. Understanding these processes requires delving deeper into how the birth of stars influences the very structure of the galaxy. One aspect of this evolving process involves the destruction and recreation of molecular clouds. The intense radiation and stellar winds from young, hot stars can strip away the gas in their vicinity, slowly dispersing the very material that once gave birth to them. This leads to a gradual thinning and eventual dissipation of the molecular cloud. Yet, star formation doesn't simply stop when clouds disperse. In fact, the material that is expelled into space can eventually contribute to new generations of stars, planets, and even life. The matter that gets thrown out during the deaths of stars, through supernovae and stellar winds, enriches the interstellar medium, creating a cycle of rebirth in the cosmos. This phenomenon is also a critical component of the chemical evolution of galaxies. Molecular clouds contain a rich variety of elements, many of which are created in the nuclear fusion reactions of stars, and others through processes like supernova explosions. These elements are then carried out into space, contributing to the creation of new stars, planetary systems, and even the building blocks of life. In this way, stellar nurseries play a crucial role not only in the formation of stars, but in shaping the chemical composition of the galaxy as a whole. It is through this constant recycling of matter that galaxies evolve, and new stars form, often with slightly different compositions than those that came before. It's also essential to understand the distinction between various types of stellar nurseries, as their properties and behaviors can vary significantly. One well-known example is the dark nebula, a type of molecular cloud that is particularly dense and cold, appearing opaque due to the dust particles blocking out the light from stars behind it. These clouds are often the birthplaces of stars, providing the ideal conditions for gas to collapse under gravity. Dark nebulae are essentially the seedbeds of star formation, where the most pristine and unperturbed gas resides, allowing for the gradual, controlled process of stellar birth. Other notable types of stellar nurseries include emission nebulae, which are clouds of gas ionized by the radiation of nearby hot stars. These regions are often rich in ionized hydrogen, H2 regions, where the intense ultraviolet light from massive stars causes the surrounding hydrogen gas to emit light in various wavelengths. The most famous example of this kind of nebula is the Orion Nebula, one of the closest and most well-studied stellar nurseries. Emission nebulae can be visually stunning, glowing in vibrant colors due to the ionization of gas, creating some of the most breathtaking images in astrophotography. There are also reflection nebulae, which do not emit their own light but instead reflect the light from nearby stars. These nebulae often have a blue or greenish hue, as dust grains in the cloud scatter shorter wavelengths of light. These types of nebulae are less commonly associated with active star formation, but they still play an important role in the overall structure of molecular clouds and the interstellar medium. The study of these different types of stellar nurseries is not just about cataloging objects in the universe. It is also about understanding the underlying physics that govern their formation, behavior, and evolution. For example, how do the magnetic fields interact with the gas in a molecular cloud to influence star formation? How do turbulence and pressure balance each other to dictate the rate at which stars are born? How do young stars interact with their surrounding environments to trigger new bursts of star formation, or conversely, halt the process entirely? These questions are at the heart of current research in astrophysics, and they are fundamental to understanding the life cycle of stars, galaxies, and the universe itself. Beyond the physics of star formation itself, stellar nurseries are crucial for understanding the broader context of galaxy formation and evolution. Studies of stellar nurseries across different regions of the universe reveal how galaxies themselves are born and evolve over time. For example, galaxies in the early universe were likely dominated by intense, rapid star formation, much of it occurring in dense, chaotic stellar nurseries. These early star-forming regions may have been far more efficient than the nurseries we see today, driven by the higher rates of gas accretion and more frequent mergers between galaxies. As the universe evolved and galaxies matured, star formation rates began to slow down, and the conditions within molecular clouds changed. Modern stellar nurseries tend to be smaller and less efficient, with gas being depleted over time. This shift in star formation efficiency has profound implications for our understanding of galaxy evolution, as it helps explain why many galaxies today are no longer producing new stars at the same rate they once did. Understanding the dynamics of stellar nurseries across cosmic time allows us to build a more complete picture of how galaxies have changed over billions of years. Stellar nurseries are also key to understanding the potential for life beyond Earth. As we continue to search for exoplanets, the study of stellar nurseries provides insight into the conditions that could support the development of habitable worlds. Many of the stars formed in these regions go on to have planets, and some of these planets may lie within the habitable zone of their host stars, the region where liquid water can exist. This means that stellar nurseries are not just places where stars are born, but also the sites where the conditions for life as we know it are established. Recent discoveries of exoplanets within the habitable zones of distant stars, many of which are formed in stellar nurseries, have reignited interest in the possibility of life elsewhere in the universe. These planets, though often very different from Earth, may possess the fundamental ingredients for life. By studying the types of stars that form in stellar nurseries and the planetary systems they create, scientists hope to find planets that may harbor life, or at least the conditions that could support it. Looking ahead, the future of stellar nursery research is incredibly exciting. As technology continues to improve, astronomers are gaining access to more powerful telescopes and observation techniques. Instruments like the James Webb Space Telescope, JWST, are expected to revolutionize our understanding of stellar nurseries. With its ability to peer deeper into space and observe regions in the infrared spectrum, JWST will provide us with unprecedented views of star-forming regions, offering insights into the earliest stages of star formation, and even allowing us to detect distant stellar nurseries from the early universe. In addition, the development of new simulation techniques and computational models is helping scientists simulate the complex interactions within molecular clouds and stellar nurseries. These simulations take into account everything from the interplay between gravity and gas pressure to the role of magnetic fields and turbulence. As our models become more sophisticated, we can better predict how different environments influence star formation, and we can test these predictions against observations made by telescopes and space probes. Ultimately, the study of stellar nurseries is not just a scientific endeavor, it's a quest to understand the very origins of the cosmos. These regions are the birthplaces of stars, the creators of planets, and the forges of the elements that make up the universe. By peering into the heart of these cosmic nurseries, we uncover the secrets of how the universe continually renews itself, creating new generations of stars and planets, and possibly even the conditions necessary for life. With each discovery, we are reminded of how much we still have to learn about the universe's most fundamental processes, and how little we know about the vast, infinite expanse that surrounds us. The journey through stellar nurseries continues as we examine how new technologies are offering unprecedented insight into these cosmic birthplaces. With advancements in observational methods, scientists are now able to examine stellar nurseries in greater detail than ever before, shedding light on their incredibly complex nature. These efforts not only help us understand the life cycle of stars but also give us the tools to map the intricate dynamics of the interstellar medium and the forces that drive star formation. One such breakthrough is the improvement in radio and infrared telescopes. While optical telescopes rely on visible light to capture images, radio and infrared wavelengths can penetrate the thick gas and dust that often obscure the heart of molecular clouds. These wavelengths provide clearer images of regions where stars are in the early stages of formation, offering vital clues about the physical conditions within these clouds. For instance, infrared observations help scientists detect the heat emitted by young stars and the surrounding gas, which are often invisible in visible light. This allows us to see through the dense nebulae and observe the precise stages of star formation that were previously hidden. Among the most significant tools for studying stellar nurseries in recent years is the Atacama Large Millimeter/Submillimeter Array, ALMA. Located in the Atacama Desert in Chile, ALMA is one of the most advanced radio telescopes in the world. It can observe the molecular clouds at the heart of stellar nurseries in high resolution, enabling scientists to examine the chemical composition, temperature, and structure of these regions. ALMA has already provided groundbreaking insights into star formation, including observing the birth of massive stars and even the interactions between young stars and their surrounding environments. Another key advancement comes from space-based observatories like the Hubble Space Telescope. Hubble has provided stunning images of stellar nurseries like the Orion Nebula and the Eagle Nebula, showcasing the intricate and colorful nebulae that form as new stars ignite. These images reveal the complex structures within these regions, including the star clusters that often form in these nurseries and the turbulent processes that shape them. Hubble's ability to capture images in visible and ultraviolet wavelengths has also provided insight into the life cycles of stars, allowing scientists to track the stages of star birth and evolution over time. The James Webb Space Telescope, JWST, represents the next frontier in space observation. Set to make groundbreaking contributions to our understanding of stellar nurseries, JWST's infrared capabilities will allow it to see into the deepest, most obscured corners of these star-forming regions. With its ability to detect faint infrared emissions from the coldest, densest regions of molecular clouds, JWST will reveal crucial information about how stars form from the very first stages of collapse to the final stages of ignition. Moreover, it will offer a better understanding of the role of dust in star formation and the complex interactions between gas, dust, and radiation within these nebulae. As we continue to push the boundaries of our technological capabilities, the impact on our understanding of stellar nurseries grows exponentially. These advancements provide us with a window into the very nature of star formation, and ultimately, the processes that shape the universe. Stellar nurseries represent the raw materials of the cosmos, the fundamental building blocks of galaxies, stars, and planets. They are the places where the universe's creative forces are most apparent, as cosmic gas and dust coalesce under gravity to form the stars that light up the night sky. However, our understanding of stellar nurseries isn't just based on advanced technology and instrumentation. It also comes from a growing body of theoretical work that explains the complex processes occurring within these regions. Astrophysicists have developed models to simulate the conditions inside molecular clouds and stellar nurseries, and these simulations are integral to understanding star formation. Theoretical models help explain how molecular clouds collapse under gravity to form stars, how magnetic fields influence star formation, and how turbulence within the clouds can trigger or suppress star formation in different regions. One area of active research is the role of magnetic fields in star formation. Magnetic fields are present throughout the interstellar medium, including in molecular clouds, and they can have a profound effect on the processes that lead to the formation of stars. These fields can provide the necessary pressure to support molecular clouds against gravitational collapse, or they can assist in the collapse by channeling gas along magnetic field lines. Recent studies using ALMA and other observatories have revealed that magnetic fields play a significant role in shaping the structure of stellar nurseries, dictating the way gas moves within the clouds and influencing where and how stars are born. Another important factor in star formation is the turbulence within molecular clouds. These clouds are not static, they are in constant motion, with gas moving at high speeds and interacting in complex ways. This turbulence can create pockets of gas that are dense enough to collapse under gravity and form stars, while other regions may remain too diffuse to undergo star formation. Researchers are now studying how turbulence interacts with the gravitational forces within molecular clouds to create areas of intense star formation. Some models even suggest that turbulence may be responsible for triggering the formation of massive stars, which are typically more difficult to form due to their size and energy requirements. Furthermore, we cannot overlook the importance of cosmic rays in the formation of stars. These high-energy particles, originating from supernovae and other cosmic events, can influence the chemistry and physics of molecular clouds. They can heat the gas within clouds, contributing to the pressure that helps prevent or delay star formation in certain regions. At the same time, cosmic rays may also trigger the collapse of molecular clouds by ionizing the gas and increasing its density. These interactions are yet another example of the interconnectedness of various cosmic forces in shaping the birth of stars. As much as we've learned about stellar nurseries, there's still a great deal of mystery surrounding these cosmic birthplaces. One of the most profound questions remaining is how stars form in a way that leads to the creation of planetary systems. While we understand the basic mechanics of star formation, the exact process by which planets emerge from the surrounding gas and dust remains a subject of intense study. It's believed that, as a star forms, it is surrounded by a protoplanetary disk, a rotating disk of gas and dust that can eventually coalesce into planets. However, the details of this process, particularly the role of turbulence, magnetic fields, and the chemical composition of the gas, are still being studied. Additionally, astronomers are investigating whether the conditions in stellar nurseries are suitable for life to form. This inquiry ties into the broader search for exoplanets and the possibility of life beyond Earth. The same stellar nurseries that give birth to stars also provide the raw materials for planetary systems, some of which may host habitable environments. The discovery of exoplanets in the habitable zones of distant stars, many of which formed in stellar nurseries, has fueled speculation about the potential for life elsewhere in the universe. Could the same chemical processes that led to life on Earth occur in other star systems born in stellar nurseries? This question remains one of the most exciting areas of research in both astronomy and astrobiology. Stellar nurseries are the heart of star formation, where the raw materials of the universe come together under the influence of gravity, magnetic fields, and other cosmic forces to create the stars and planetary systems that populate galaxies. These regions are not static or predictable. They are constantly evolving, shaped by the complex interactions between gas, dust, radiation, and stellar winds. As our understanding of these processes deepens, we are not only uncovering the mysteries of star birth but also gaining insight into the broader workings of the universe. Stellar nurseries are the cradles of creation in the cosmos, and their study continues to inspire awe and wonder as we unlock the secrets of the stars. As we continue exploring the mysteries of stellar nurseries, it's important to delve deeper into the broader implications of understanding these star-forming regions. Stellar nurseries are not just isolated pockets in the universe. They are dynamic, interconnected ecosystems that contribute to the overall structure and evolution of galaxies. By studying how stars form, grow, and eventually die, we learn more about the life cycle of galaxies themselves. The process of star formation is often triggered by external events, such as the shockwaves from nearby supernovae or the collision of molecular clouds. These shocks can compress gas within a cloud, increasing its density and initiating the collapse of the cloud under its own gravity. This triggers the birth of new stars. The interaction of these newborn stars with the surrounding gas and dust also plays a vital role in shaping the evolution of a galaxy. The energy and radiation emitted by stars can ionize surrounding gas, creating nebulae and fueling further star formation in some regions, while suppressing it in others. This delicate balance between star formation and star destruction is crucial in maintaining the cyclical nature of a galaxy's life. This process also highlights the interconnectedness between star-forming regions and other cosmic phenomena. For instance, the death of massive stars, through supernova explosions or the formation of black holes, releases heavy elements into the interstellar medium. These elements, including carbon, oxygen, and iron, enrich the surrounding gas clouds, providing the building blocks for future generations of stars, planets, and possibly even life. It's through this cycle of birth and death that galaxies evolve, with each new generation of stars being born from the remnants of their predecessors. This never-ending cycle is often referred to as the stellar life cycle. In addition to this cyclical process, stellar nurseries play a crucial role in regulating the overall star formation rate within galaxies. The presence of large molecular clouds, the ongoing processes of gas compression and heating, and the dynamics between turbulence and gravity all contribute to the balance between star formation and quenching. In some galaxies, star formation is actively promoted, leading to a steady influx of new stars. In others, star formation is suppressed due to factors like high levels of cosmic radiation, the effects of supermassive black holes, or a lack of available gas. Moreover, the study of stellar nurseries and star formation is key to understanding galactic evolution on larger timescales. Galaxies are constantly changing and evolving over billions of years, and the rate at which stars are formed in these regions has a direct impact on the overall shape and makeup of the galaxy. For example, galaxies that form stars more rapidly tend to be spiral galaxies, with a vibrant mix of new and old stars. Meanwhile, galaxies with low star formation rates, such as elliptical galaxies, are dominated by older, less active stars. Understanding these star-forming processes gives astronomers valuable clues about how galaxies evolve and how their environments shape the stars within them. Beyond the immediate life cycle of stars, stellar nurseries also offer clues about the broader history of the universe. The study of the oldest and most distant stellar nurseries allows astronomers to look back in time, investigating the conditions of star formation in the early universe. By examining the first galaxies to form stars, astronomers can gain insight into the early stages of the universe itself, how it transitioned from the primordial soup of gas and dust to the richly varied collection of stars, planets, and galaxies we see today. One key aspect of stellar nurseries that has been the focus of much recent research is the birth of massive stars. These stars, which can have many times the mass of our Sun, are essential for the development of galaxies. However, they are much more difficult to study, as they are often surrounded by thick clouds of gas and dust that obscure our view. Massive stars also have very short lifespans, burning through their fuel quickly and exploding as supernovae within just a few million years. Despite this, they are crucial for understanding the evolution of galaxies, as their intense radiation and powerful stellar winds influence the surrounding interstellar medium, triggering further star formation and driving the dynamics of the galaxy. The birth of these massive stars is thought to be linked to the process of feedback. Feedback refers to the ways in which the energy and material produced by stars impact their surroundings, often driving further changes in the stellar nursery itself. The radiation from young stars can heat nearby gas, preventing it from collapsing further and slowing the rate of star formation in that region. However, this feedback can also trigger new star formation in other parts of the cloud, leading to a dynamic, ever-evolving system. This process is especially important in the context of massive stars, whose feedback can dramatically alter the environment of their stellar nurseries, influencing the types of stars that form in the future. The role of feedback is further complicated by the presence of cosmic magnetic fields. Magnetic fields within molecular clouds can regulate the flow of gas and dust, influencing the collapse of clouds and the formation of stars. In some cases, magnetic fields can prevent clouds from collapsing entirely, suppressing star formation. In other cases, they may funnel gas towards certain regions of the cloud, promoting the birth of stars in those areas. Understanding the role of magnetic fields is a crucial part of piecing together the complex puzzle of star formation, as these fields are often the unseen drivers behind many of the processes that shape stellar nurseries. The ongoing study of stellar nurseries is also bringing us closer to understanding the potential for life elsewhere in the universe. The same processes that lead to the formation of stars also create the conditions for planets to form. As stars are born, they are surrounded by rotating disks of gas and dust known as protoplanetary disks. These disks are the birthplace of planets, and studying their formation and evolution helps astronomers understand how planetary systems come together. By examining the conditions in which stars and planets form, scientists are exploring whether the same conditions could exist elsewhere in the universe, potentially leading to the discovery of habitable planets beyond our solar system. Stellar nurseries, then, are not just fascinating objects of study, they are also the key to understanding the bigger picture of the universe. They provide insight into how galaxies evolve, how stars live and die, and how planets and potentially life can emerge. As we continue to unlock the mysteries of these star-forming regions, we are not only gaining a better understanding of our own origins, but also opening the door to the possibility of life elsewhere in the cosmos. As technology continues to advance, the future of stellar nursery research looks incredibly promising. Instruments like the James Webb Space Telescope, along with advancements in ground-based observatories, will allow us to peer deeper into the universe than ever before. These tools will provide us with new ways to observe the birth of stars, track their development, and understand how they influence the galaxies around them. The insights gained from these studies will likely continue to reshape our understanding of the universe, offering new revelations about the processes that govern the cosmos. The study of stellar nurseries is a journey into the heart of creation itself. These cosmic birthplaces are where the elements of life and the foundations of the universe come together, where the raw materials of the cosmos are transformed into the stars that light our way. And as we continue to explore these fascinating regions, we are reminded of the vast, interconnected web of forces that shape our universe, from the smallest atoms to the largest galaxies. Each new discovery brings us one step closer to understanding the intricate, beautiful complexity of the cosmos, and our place within it. As we move deeper into the intricacies of stellar nurseries, it's important to consider the ongoing advancements in both observational and computational technologies. With each breakthrough in technology, our ability to examine these stellar birthplaces becomes more precise and comprehensive. For example, with the arrival of space-based observatories like the James Webb Space Telescope, JWST, we now have the unprecedented ability to peer through the dense clouds of dust and gas that obscure many star-forming regions in visible light. This capability has opened up new avenues of research, enabling us to observe the exact conditions under which stars are born in unprecedented detail. Through infrared imaging, the JWST can capture the faint glow of young stars still in the process of formation, surrounded by their protoplanetary disks. This ability allows scientists to track the early stages of star formation, monitoring the accretion of gas and dust as it spirals inward toward the nascent star. It also allows astronomers to observe the cooling phase of gas and dust in these regions, providing key insights into the physical properties and chemical composition of the molecular clouds that give rise to stars. By combining these observations with data from other instruments, such as radio telescopes and X-ray observatories, researchers can create a more complete picture of star formation and the broader dynamics at play in stellar nurseries. One exciting area of research in stellar nurseries involves the study of high-mass stars, those that are much larger than our Sun. These stars are crucial for understanding the chemical enrichment of the universe, as their explosive deaths and supernovae scatter heavy elements like carbon, oxygen, and iron across space. These elements are then incorporated into future generations of stars, planets, and even life itself. However, studying the formation of these massive stars has proven to be a significant challenge, as they are often born in the densest parts of molecular clouds, making them difficult to observe directly. With advances in imaging and spectroscopic techniques, astronomers are now able to gather more data about how these stars form and how their intense radiation and stellar winds influence their surroundings. In particular, massive stars are thought to form in a somewhat different process compared to smaller stars. While low and intermediate mass stars like our Sun form through the gradual collapse of gas within molecular clouds, massive stars may form in clusters of gas and dust, with the initial collapse driven by the gravitational attraction of other gas clumps. This clustering effect could lead to the formation of multiple massive stars in close proximity to one another, creating environments of intense stellar feedback. Understanding how these massive stars form and interact with their surroundings is critical for unraveling the complexities of galaxy evolution, as these stars play a major role in shaping the interstellar medium and triggering subsequent waves of star formation. Additionally, the study of stellar nurseries sheds light on the physical conditions that govern star formation. For example, molecular clouds, where stars are born, are often cold and dense, with temperatures just above absolute zero and pressures much higher than those found in the interstellar medium. These conditions allow hydrogen molecules to exist in their most stable form, providing the raw material for star formation. However, even within these cold, dense clouds, there is significant turbulence, driven by a variety of forces, including the motions of gas, the impact of stellar winds, and the presence of magnetic fields. This turbulence plays a crucial role in shaping the formation of stars, as it can both promote and inhibit the collapse of gas into clumps that eventually form stars. Understanding the balance between turbulence and gravity in these environments is one of the ongoing challenges in stellar formation research. The role of magnetic fields in stellar nurseries is another important area of study. Magnetic fields are thought to influence the process of star formation in multiple ways. They can help regulate the collapse of molecular clouds, providing additional support to prevent the gas from collapsing too quickly. On the other hand, magnetic fields can also channel gas into certain regions, fostering the growth of dense, star-forming clumps. These magnetic effects can ultimately affect the properties of the stars that form, influencing everything from their mass to the way they interact with the surrounding gas and dust. Understanding the interplay between magnetic fields and other factors, such as turbulence and gravity, is crucial for creating accurate models of star formation. One of the most stunning features of stellar nurseries is the nebulae they produce. These nebulae are vast clouds of gas and dust that are illuminated by the young, hot stars at the heart of the nursery. The light from these stars ionizes the surrounding gas, causing it to glow in various colors. Some of the most famous nebulae, such as the Orion Nebula and the Eagle Nebula, are stellar nurseries in action, where stars are being born within the heart of these luminous clouds. Nebulae can be classified into several types, including emission nebulae, reflection nebulae, and dark nebulae, each with its own distinct characteristics. Emission nebulae, like the Orion Nebula, are bright and colorful due to the ionization of hydrogen atoms by the radiation from nearby stars. These nebulae are often the most visible and most studied, as they represent the most active and energetic phase of star formation. Reflection nebulae, on the other hand, are cooler and dimmer, reflecting the light of nearby stars without emitting their own light. These nebulae often appear blue due to the scattering of light by dust particles, similar to the way the Earth's sky appears blue during the day. Dark nebulae, as the name suggests, are opaque clouds of gas and dust that obscure the light from background stars, making them appear as dark patches against the brighter sky. In addition to providing beautiful visuals, nebulae also serve as laboratories for studying the processes of star formation. The physical conditions in these nebulae, such as temperature, density, and composition, offer insights into how stars and planetary systems are formed. By studying the emission and absorption lines in the light from nebulae, astronomers can gather information about the chemical composition of the gas and dust within these regions. This data can help scientists understand the building blocks of stars, planets, and other celestial bodies, as well as the conditions required for life to exist elsewhere in the universe. The study of stellar nurseries also has practical implications for our understanding of other parts of the universe. For example, understanding how stars form in dense, dusty clouds could help explain how star formation occurs in galaxies far beyond our own. In addition, the study of stellar nurseries provides insight into the formation of planetary systems. As stars form, they are often surrounded by disks of gas and dust known as protoplanetary disks. These disks contain the raw materials for planet formation, and by studying them, astronomers can gain valuable information about the processes that lead to the creation of planets. Understanding the formation of planetary systems is essential for identifying exoplanets that may harbor life, as it helps scientists pinpoint the conditions required for habitable environments. In the distant future, as more powerful telescopes and instruments come online, we will likely gain an even greater understanding of stellar nurseries and the processes that govern star formation. By exploring these cosmic birthplaces, we continue to unravel the mysteries of the universe and our place within it. With each discovery, we come closer to answering some of the most fundamental questions about the nature of the cosmos, and the ongoing journey of exploring these enigmatic regions will continue to captivate and inspire humanity for generations to come. As our exploration of stellar nurseries continues, we delve even further into the fascinating dynamics that govern star formation. With each advancement in technology, our understanding of how stars are born and evolve becomes more refined, and new questions emerge. One such question revolves around the influence of large-scale structures in the universe, such as galaxies, on the star formation process within stellar nurseries. Galaxies themselves are vast cosmic structures composed of billions of stars, gas, dust, and dark matter. The rate at which stars form within these galaxies is not uniform, with certain regions, particularly spiral arms, experiencing higher rates of star formation than others. In these star-forming regions, stellar nurseries can be found in abundance, creating new stars at an astonishing pace. But how do these large-scale structures impact the smaller, more localized processes occurring within molecular clouds? One of the key factors that influences star formation in these dense regions is the gravitational pull exerted by the larger galaxy. In a spiral galaxy, for example, the spiral arms are regions of higher density, and the gravitational forces in these areas can compress molecular clouds, triggering star formation. These gravitational interactions, known as tidal forces, play a crucial role in the evolution of stellar nurseries. When molecular clouds pass through regions of intense gravitational influence, they may experience a compression of gas and dust, creating localized regions where new stars can be born. This process, known as cloud compression, is thought to be a significant driver of star formation in galaxies, particularly in environments with high levels of gravitational interaction. Furthermore, the activity of massive stars themselves can influence the surrounding star-forming regions. Stellar winds and radiation from young, hot stars can compress and disrupt nearby gas clouds, triggering new cycles of star formation. This feedback mechanism, where stars and their surrounding environments interact in a constant dance of creation and destruction, is a vital part of understanding the life cycle of molecular clouds and the long-term evolution of galaxies. As massive stars explode in supernovae, they send shockwaves through their surrounding environments, clearing away the gas and dust that may have been feeding the formation of new stars. This dramatic process can temporarily halt star formation, but the remnants of these explosive events can later serve as the building blocks for new generations of stars and planets. Another intriguing aspect of stellar nurseries is the role of dark matter in star formation. Dark matter, an invisible and mysterious substance that makes up the majority of the universe's mass, does not interact with light or other forms of electromagnetic radiation, making it incredibly difficult to detect. However, its gravitational effects on visible matter, including gas clouds, can have a profound impact on the dynamics of star formation. In some regions of the universe, dark matter is thought to form vast halos around galaxies, exerting a gravitational pull that can influence the behavior of molecular clouds within stellar nurseries. The precise role of dark matter in star formation remains a subject of ongoing research, but its potential influence cannot be overlooked as we continue to unravel the mysteries of stellar nurseries and the broader cosmos. On a more localized scale, the interaction of stars within a nursery can lead to the formation of planetary systems. As young stars gather surrounding gas and dust, a portion of this material may begin to coalesce into planetary bodies. These protoplanetary disks, composed of dust, ice, and gas, are the birthplace of the planets, moons, and other objects that will eventually orbit a star. The formation of these disks is a delicate process, influenced by the gravitational interactions between the star and its surroundings. Over time, the material within the disk clumps together to form planetesimals, which can eventually grow into full-fledged planets. The study of protoplanetary disks is another crucial component of understanding stellar nurseries. By examining the properties of these disks, such as their temperature, composition, and structure, scientists can gain insights into the processes that lead to the formation of planets. Some of the most exciting discoveries in this area come from observing young stars that are still in the process of forming their planetary systems. With the help of advanced telescopes and instruments, astronomers have been able to detect the faint signatures of these protoplanetary disks, providing valuable clues about how planets, moons, and even complex life forms may arise. This understanding of planet formation ties directly into the broader search for habitable worlds beyond our solar system. As we explore distant star systems, we are not only looking for signs of life but also for planets that could potentially support life as we know it. The composition of a planet's atmosphere, its distance from its parent star, and its ability to retain liquid water are all critical factors in determining whether a world could be habitable. As our knowledge of stellar nurseries grows, so too does our ability to identify the conditions that might give rise to planets capable of supporting life. One particularly intriguing area of research involves the study of star-forming regions in other galaxies. By observing distant stellar nurseries, astronomers can study the process of star formation in environments that differ significantly from our own galaxy. These observations provide valuable insights into how star formation occurs in different cosmic contexts, from the dense and active regions of starbursts to the more quiescent, isolated regions found in some galaxies. By comparing star formation across different galaxies, researchers can develop a more comprehensive understanding of the factors that influence stellar birth and how these factors might change over time. The study of stellar nurseries also has important implications for our understanding of the early universe. In the first few billion years after the Big Bang, galaxies were forming stars at an incredibly rapid rate. These early stellar nurseries played a crucial role in the development of galaxies, providing the building blocks for the first generations of stars, planets, and other celestial bodies. As we look farther back in time, through the study of distant galaxies and the cosmic microwave background radiation, we can piece together a picture of how the earliest stars were born and how they evolved into the complex structures we observe today. As our ability to observe the universe continues to improve, we are likely to uncover even more secrets about the nature of stellar nurseries and the forces that drive star formation. The advent of next-generation telescopes, such as the James Webb Space Telescope and the Extremely Large Telescope, promises to provide even more detailed and high-resolution images of these cosmic birthplaces, allowing us to observe the formation of stars in real time. With each new discovery, we gain a deeper understanding of the processes that shape the universe and the stars that light up the night sky. The study of stellar nurseries is not just about understanding how stars form. It is about understanding the very building blocks of the universe itself. These regions are where the raw materials of the cosmos come together to create the stars, planets, and galaxies that make up our universe. They are the places where the conditions for life, both as we know it and in forms we have yet to imagine, may one day be created. And as we continue to explore these fascinating regions, we are not just learning about the birth of stars, but also about the origins of everything we see around us, from the planets we call home to the very elements that make up our bodies. Stellar nurseries are, in many ways, the heart of the universe, and they continue to inspire awe, wonder, and discovery for those of us who seek to understand the cosmos. As we continue our exploration of stellar nurseries, we find that one of the most fascinating aspects of these cosmic birthplaces lies in their incredible diversity. Not all stellar nurseries are the same, and they can vary dramatically in terms of size, density, and the types of stars they produce. This variation plays a significant role in shaping the evolution of galaxies and the broader structure of the universe. Some stellar nurseries are enormous, spanning vast regions of space. These giant molecular clouds can be hundreds or even thousands of light-years across and contain trillions of stars waiting to be born. The largest of these clouds, known as giant molecular clouds, GMCs, are the most prolific sites of star formation in galaxies. They can hold enough mass to form millions of stars, and many of them exist in the spiral arms of galaxies, where gravitational forces trigger the collapse of gas and dust into dense knots, initiating the process of star formation. These GMCs are also the birthplaces of the most massive stars, giants that will burn hot and bright for only a short time before exploding in supernovae, enriching the interstellar medium with heavy elements that are essential for the creation of planets and life. Other stellar nurseries are much smaller, localized regions of space where star formation occurs at a slower pace. These low-mass stellar nurseries may only produce a few stars at a time, but they are no less important to our understanding of the cosmic cycle. In fact, many of the stars that we see in the night sky today, our Sun included, likely formed in such smaller, less dramatic nurseries. These stars are typically cooler, smaller, and longer-lived than their massive counterparts, and their formation is often more gradual. Over time, they accumulate enough mass to form stable, main-sequence stars that can burn for billions of years, providing the steady light and heat that sustain life on planets like Earth. Another crucial aspect of stellar nurseries is the process of feedback. As stars are born, they begin to exert their influence on the surrounding environment, triggering complex interactions that shape the future of the nursery. The feedback mechanisms at play can be divided into two primary categories: positive feedback and negative feedback. Positive feedback occurs when new stars, particularly the massive ones, accelerate the process of star formation in the surrounding cloud. These stars emit intense radiation and powerful stellar winds, which can compress nearby gas clouds, causing them to collapse and form new stars. In this way, the birth of one generation of stars can create the conditions for the formation of the next. This is especially true in star-forming regions that are already rich in gas and dust, where the feedback from young stars can lead to a chain reaction of star birth. Negative feedback, on the other hand, occurs when the energy and radiation from newly formed stars disrupt the very cloud that gave rise to them. As massive stars age and explode in supernovae, they release enormous amounts of energy, which can blow away surrounding gas and dust, halting the formation of new stars. In some cases, this feedback can even cause a molecular cloud to dissipate entirely, preventing further star formation in that region. This cyclical process of star formation and destruction plays a key role in regulating the rate of star formation within a galaxy, and can have significant implications for the overall structure of galaxies. As we've explored, stellar nurseries are often associated with nebulae, vast clouds of gas and dust that give birth to stars. These nebulae are not just beautiful to look at, they also hold critical clues about the conditions that lead to star formation. When we observe nebulae through powerful telescopes, we can see how the gas and dust within these clouds clump together under the influence of gravity. These regions of high density are the birthplaces of new stars, and their colors and structures reveal much about the physical processes at work. One of the most famous types of nebulae associated with stellar nurseries is the emission nebula. These nebulae shine brightly because of the intense ultraviolet radiation emitted by young, hot stars. As this radiation interacts with the surrounding gas, it ionizes the atoms, causing them to emit light at specific wavelengths. This creates the colorful, glowing regions we see in images of stellar nurseries. The most famous example of an emission nebula is the Orion Nebula, located just 1,500 light-years from Earth. This nebula is one of the most studied regions of star formation, and its glowing gas and dust provide a spectacular view of the processes at work within a stellar nursery. Another important type of nebula associated with star formation is the reflection nebula. Unlike emission nebulae, reflection nebulae do not emit their own light. Instead, they shine because they reflect the light of nearby stars. These nebulae are often composed of smaller dust particles, which scatter the light from stars and give the nebula its characteristic bluish hue. Reflection nebulae are typically found near young stars and are often located in regions where star formation is just beginning. Dark nebulae, on the other hand, are dense clouds of gas and dust that block the light from stars behind them. These nebulae are often found in the densest regions of molecular clouds, where the conditions for star formation are most favorable. Dark nebulae appear as dark patches against the backdrop of brighter stars or emission nebulae. While they may seem ominous, dark nebulae are essential to the process of star formation, as they provide the material needed for new stars to form. In recent years, advances in observational technology have allowed scientists to study stellar nurseries in greater detail than ever before. Instruments like the Atacama Large Millimeter/Submillimeter Array, ALMA, and the James Webb Space Telescope, JWST, are helping astronomers observe the formation of stars in unprecedented detail. These telescopes can capture images of stellar nurseries in different wavelengths of light, including infrared and millimeter wavelengths, allowing scientists to peer through the dense gas and dust that often obscures our view of the star-forming process. One of the most exciting discoveries made with these new technologies is the observation of protostars, the early stages of star formation. A protostar is a young star that is still gathering mass from its surrounding gas and dust. These objects are incredibly difficult to detect, as they are often hidden within the dense clouds of gas and dust in which they form. However, by observing the heat emitted by these objects in infrared wavelengths, astronomers have been able to uncover a wealth of information about the conditions that lead to the birth of stars. As we continue to explore stellar nurseries, we are also learning more about the role that these regions play in the broader evolution of galaxies. Star formation is not a static process. It is deeply connected to the life cycles of galaxies themselves. As galaxies grow and evolve, the rate at which stars form changes over time. Stellar nurseries are the engines that power this process, and understanding how they work is crucial to understanding the past, present, and future of our universe. The interaction between stellar nurseries and the broader intergalactic medium is another area of active research. The intergalactic medium is the diffuse gas that exists between galaxies, and it plays a crucial role in the evolution of star-forming regions. Some of the gas and molecular clouds may originate from the intergalactic medium, while other material may be expelled from star-forming regions and injected into the broader galaxy. The flow of gas and matter between galaxies and their stellar nurseries can have profound implications for the rate of star formation and the overall structure of the universe. In the future, as our observational capabilities continue to improve, we may be able to observe even more distant stellar nurseries, allowing us to study the process of star formation at earlier and earlier stages in the history of the universe. By understanding the birthplaces of stars, we gain valuable insights into the fundamental processes that govern the evolution of galaxies, the formation of planets, and the conditions that make life possible. The mysteries of stellar nurseries are far from being fully unraveled, and there is still much to discover. As we continue to peer deeper into these cosmic birthplaces, we may find answers to some of the most fundamental questions about the universe. How do stars form? How do galaxies evolve? And what role do stellar nurseries play in the creation of the very elements that make up life? As we explore these questions, we uncover more than just the secrets of stars. We uncover the very nature of the cosmos itself. As we venture further into the complexities of stellar nurseries, it's essential to understand how they shape not only the stars they birth but the future of galaxies and the very fabric of space itself. The intricate dynamics within these cosmic factories extend far beyond the visible birth of stars and encompass a vast array of phenomena that influence everything from planetary formation to the chemical evolution of the universe. One of the most profound aspects of stellar nurseries is the way in which the process of star formation affects the molecular clouds in which they reside. When a new star is born, it doesn't simply sit quietly in its cloud. The birth of stars, especially the massive ones, leads to a flurry of activity in its surrounding environment. This activity, often referred to as feedback, can have a dramatic impact on the gas and dust around the young star, triggering a cascade of reactions that can either enhance or inhibit further star formation. For example, massive stars, those with many times the mass of our Sun, emit powerful radiation that heats the surrounding gas and dust. This intense radiation, along with the winds of charged particles emitted by these stars, can push against the molecular cloud, dispersing gas and dust into space. In some cases, this can halt star formation altogether, as the material necessary for new stars to form is no longer present. But in other instances, the process may work in the opposite direction. The radiation can compress nearby gas, triggering a chain reaction that causes more parts of the cloud to collapse and form additional stars. This delicate balance of creation and destruction, of birth and death, is what keeps stellar nurseries in constant flux. The supernovae of massive stars are particularly significant in this regard. When a star with a mass greater than 8 times that of the Sun exhausts its nuclear fuel, it can no longer support its own weight, causing it to collapse under the force of gravity and explode in a violent supernova. These explosions release enormous amounts of energy, including high-energy photons and cosmic rays, which can spread throughout the surrounding molecular cloud. The shockwaves generated by the supernova can compress nearby regions of gas, sparking the formation of new stars. On the flip side, the supernova also injects heavy elements into the interstellar medium, enriching the gas that will eventually go on to form future generations of stars and planets. This cycle of stellar birth, death, and rebirth is essential to the life cycle of galaxies. Stars are the engines that drive the chemical evolution of the universe. Every time a star forms and undergoes fusion, it creates new elements like carbon, oxygen, nitrogen, and iron, that are critical for the formation of planets and life as we know it. When a star dies, particularly in a supernova explosion, it scatters these elements across the galaxy, where they mix with other gas and dust to form new stars and planetary systems. This process, known as stellar nucleosynthesis, is the mechanism by which the raw materials for life are spread throughout the cosmos. Interestingly, the cycle of star formation and death also plays a role in the formation of galaxies. Stellar nurseries are often found in the spiral arms of galaxies, where gas and dust are abundant. In these regions, the process of star formation is vigorous, and the birth of new stars can lead to the growth of the galaxy. However, as stars age and die, the material they eject into space can alter the dynamics of the galaxy itself. The feedback from dying stars, including supernovae and stellar winds, can trigger the formation of new stars in other parts of the galaxy, or it can halt star formation by dispersing the gas and dust needed to fuel it. This complex interplay between star birth, death, and the surrounding environment helps shape the evolution of galaxies over time. The study of stellar nurseries also brings us closer to understanding the formation of planetary systems. Our own solar system, for example, likely formed from a molecular cloud that collapsed under its own gravity, triggering the formation of the Sun and the planets. This process, called the solar nebula theory, suggests that the same materials present in stellar nurseries, gas, dust, and heavy elements, are responsible for the formation of planetary systems. By studying stellar nurseries in other galaxies, astronomers can learn more about how planets like Earth are formed and what conditions are necessary for life to emerge. One particularly fascinating discovery is the observation of planets forming within the dusty disks around young stars. These disks, known as protoplanetary disks, are composed of gas, dust, and ice, and they provide the material needed for planet formation. As a young star begins to form, it gathers mass from its surrounding cloud of gas and dust. The material that doesn't fall into the star forms a disk around it, where small particles collide and stick together, eventually forming larger bodies that can grow into planets. The study of these disks in stellar nurseries gives us important clues about how planets form and evolve. In recent years, astronomers have also discovered the existence of circumstellar habitable zones, regions around stars where conditions might be just right for life to exist on orbiting planets. These zones are of particular interest because they help us understand where life might be able to thrive beyond Earth. While the exact conditions required for life remain a subject of intense study, stellar nurseries are crucial in shaping these zones by providing the raw materials for planet formation. The ongoing exploration of exoplanets, planets that orbit stars beyond our own solar system, has revealed that many of these planets are located within their star's habitable zone. This raises the exciting possibility that life may exist elsewhere in the universe, born in the very same stellar nurseries that created our Sun. As we continue to study these birthplaces of stars, it becomes clear that stellar nurseries are not only the starting point for stars and planets, but also the cornerstone of galactic evolution. The processes at work within these regions are far-reaching, affecting everything from the distribution of elements in the universe to the formation of the very structures that make up galaxies, stars, and planets. The birth of stars is a spectacularly beautiful process, but it's also one of the most fundamental aspects of the universe. It is through the creation of stars and planets that the universe becomes habitable and capable of supporting life. Every new star born in a stellar nursery is a reminder that we are part of a much larger cosmic story, a story that has been unfolding for billions of years and will continue long after we are gone. Through the study of stellar nurseries, we not only learn about the birth of stars but also about the origins of life, the chemical evolution of the universe, and the forces that govern the cosmos. Looking to the future, the continued advancement of space telescopes and other observational tools will allow us to peer even deeper into stellar nurseries, uncovering secrets about the processes of star formation and planetary creation that were once hidden from view. The James Webb Space Telescope, for instance, is already providing breathtaking images of star-forming regions, offering new insights into the delicate balance between creation and destruction that defines stellar nurseries. With each new discovery, we move closer to answering some of the most profound questions in science. How do stars form? How do planets arise from the dust of collapsed clouds? And ultimately, how do these processes give rise to life itself? As we venture deeper into space, our understanding of stellar nurseries will continue to evolve, revealing the intricacies of the cosmos in ways that were once unimaginable. The mysteries of star birth are far from being fully unlocked, and there is still so much to learn about the forces that shape our universe. The mysteries of stellar nurseries are not only about how stars and planets are born but also about how they interact with the surrounding environment. The feedback from star formation plays a critical role in the evolution of the gas and dust clouds where these stars are created. Stellar nurseries are often dynamic and ever-changing regions of space, where new stars and planets are constantly emerging while older ones are dying. Understanding the full scope of these regions means exploring the feedback loops that occur within them, and how these processes impact their surrounding environments. The way new stars are born can be compared to a pressure cooker. When regions within molecular clouds collapse under the force of gravity, they create dense, hot cores that can eventually ignite to become new stars. However, the process isn't as simple as a gas cloud simply turning into a star. As the cloud contracts, it heats up, and certain areas within it can trigger rapid bursts of energy, leading to the formation of new stars. This energy, known as radiation pressure, can actually halt the collapse of surrounding gas, inhibiting the formation of additional stars in that particular region. Yet, these feedback mechanisms don't always lead to star formation stopping. Rather, they may cause the cloud to fragment, forming new regions where star formation can continue. In some stellar nurseries, particularly those in the process of creating massive stars, the feedback becomes so intense that it can lead to the formation of a hot, energetic bubble in the center of the cloud. This bubble, called the H2 region, is formed by the intense ultraviolet radiation emitted by young, hot stars. These regions are marked by high temperatures and an absence of neutral hydrogen, the primary constituent of molecular clouds. The H2 regions are important because they represent the moment when a young star or group of stars begin to alter their environment dramatically, shaping the future of their molecular cloud. In fact, these regions are often home to some of the most well-known nebulae we observe in space, such as the famous Orion Nebula, where new stars are continually being formed. Interestingly, the influence of massive stars can sometimes be detrimental to the formation of other stars within the nursery. As these stars age, they can explode in supernovae, releasing a massive amount of energy that pushes the gas and dust outward. This process can clear the surrounding area of material, which in turn can trigger a decrease in the rate of new star formation. Yet, supernovae can also have positive effects. The shockwaves from these explosions can compress nearby gas clouds, initiating the collapse of new regions within the molecular cloud and spurring the birth of even more stars. It's a balancing act, a cosmic dance where creation and destruction work hand in hand. The discovery of stellar nurseries has been greatly enhanced by the development of advanced observational tools. While optical telescopes have long allowed us to peer into the visible universe, much of the activity within stellar nurseries takes place in wavelengths that are invisible to the naked eye. For example, infrared telescopes, such as the Spitzer Space Telescope, allow us to see through the dense gas and dust that often obscures our view of star-forming regions. These observations reveal the true nature of stellar nurseries and the processes occurring within them, showing the birth of stars in great detail. One of the most striking features that we can observe in these regions is the formation of planetary systems. When gas and dust form around a young star, it doesn't just remain as a cloud. Instead, the material begins to condense and clump together, forming larger and larger objects. These objects eventually grow into planets, moons, and other bodies. This process is particularly important because it is through this very same mechanism that our own solar system formed. Observations of stellar nurseries in other galaxies help us understand not only how stars are born but how planetary systems come into being and what factors influence their formation. In fact, the study of protoplanetary disks in stellar nurseries has revealed fascinating insights into the conditions required for planet formation. For example, astronomers have found that the composition of the disk, how much gas, dust, and ice it contains, plays a key role in determining what kinds of planets can form. In regions where the disk contains large amounts of ice, it is easier for rocky planets to form, as the ice acts as a glue, helping dust particles stick together. On the other hand, in regions with little ice, it may be more difficult for rocky planets to form, and gas giants like Jupiter may be more likely to form instead. Additionally, observations of the chemical makeup of these disks have shown that many of the elements that are essential for life, such as carbon, oxygen, and nitrogen, are present in molecular clouds long before the stars they surround are born. These elements are crucial for the formation of water, organic molecules, and even the building blocks of life. This has profound implications for the search for extraterrestrial life, as it suggests that the conditions necessary for life may exist on planets orbiting other stars, even in distant galaxies. The fact that these elements are so readily available in stellar nurseries indicates that the building blocks for life may be common throughout the universe. In recent years, the discovery of exoplanets, planets orbiting stars outside of our solar system, has opened up new frontiers in the study of stellar nurseries. The study of these exoplanets and their formation processes has given scientists the ability to test theories about how planetary systems are formed and how they evolve over time. By observing the characteristics of exoplanets, such as their size, composition, and distance from their star, astronomers can gain insight into the conditions within the protoplanetary disks that gave rise to them. Furthermore, studying the atmospheres of these exoplanets can reveal information about the types of gases that were present in the disks, helping to paint a clearer picture of how life-supporting planets might form. One of the most exciting aspects of studying stellar nurseries is that they provide us with a glimpse into the future of our own solar system. Our Sun, which was born from a molecular cloud billions of years ago, will eventually exhaust its nuclear fuel and undergo a transformation into a red giant before shedding its outer layers and leaving behind a dense core known as a white dwarf. This process will happen over the course of billions of years, but by studying the ongoing birth and death of stars in other parts of the galaxy, we gain valuable insight into the long-term evolution of our own Sun and the solar system. While stellar nurseries continue to captivate scientists and astronomers, they also raise profound questions about the origins of life itself. What conditions are necessary for life to emerge? How do the materials needed for life come together in the right ways? These questions are at the heart of astrobiology, the study of life in the universe. The study of stellar nurseries is an integral part of this field, as it helps us understand how the building blocks of life are formed and spread throughout the cosmos. The discovery of life beyond Earth remains one of the most tantalizing prospects in science, and the study of stellar nurseries brings us one step closer to answering that age-old question: are we alone in the universe? In conclusion, stellar nurseries are more than just the birthplaces of stars. They are the cosmic workshops where the building blocks of galaxies, planets, and even life itself are forged. Through the process of star formation, the raw materials of the universe are transformed into the stars and planetary systems that make up the vast, complex cosmos we observe today. These regions are essential not only for understanding the formation of stars and planets, but also for exploring the origins of life and the future of our own solar system. As we continue to study these mysterious regions, we unlock the secrets of the universe and uncover the forces that shape the very fabric of space and time. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.